What if I told you that right now, somewhere in the universe, time is moving backward, or that for some unlucky traveler falling into a black hole, the entire future of the cosmos could flash before their eyes in mere seconds? Time, that steady ticking on your wristwatch, is anything but constant when you step beyond our little corner of space. Einstein shattered our everyday notions of time over a century ago with his twin paradox. Imagine one twin rockets off at near light speed and returns younger than their earthbound sibling. But that's just the tip of the cosmic iceberg. Out there in the vastness, time stretches, loops, and even shatters entirely under the universe's extreme rules. Black holes twist it like taffy, distant galaxies appear frozen in their past, and the very first moments after the Big Bang might hold clues to time's true nature, if it even existed before the universe began. Today, we're diving into 30 mind-bending facts that'll warp your sense of time more than a black hole's gravity. You'll discover why time might flow backward in certain quantum realms, how entire civilizations could rise and fall in the blink of an eye from a cosmic perspective, and why some physicists suspect time itself could be an illusion, a trick of perception woven into the fabric of reality. These aren't just abstract theories, they're real phenomena shaping everything from the fate of stars to the way your GPS works. The universe operates on a timescale so grand and strange that it makes our human clocks seem laughably simplistic. So why does any of this matter? Because time isn't just a clock on the wall, it's the hidden scaffolding of existence. Understanding its mysteries means peering into the heart of reality itself, from the quantum foam of the smallest particles to the accelerating expansion of the cosmos. By the end of this journey, you'll never look at a second, a sunset, or the night sky the same way again. The universe has been playing tricks with time for billions of years, and we're just beginning to uncover the rules of the game. Time behaves like a stretchy fabric around massive objects, literally slowing down where gravity pulls hardest. This isn't science fiction, it's Einstein's general relativity in action. Picture two identical clocks, one placed at sea level and the other on top of Mount Everest. Over years, the sea level clock would fall slightly behind because Earth's gravity tugs harder there, warping time itself. The difference is tiny, just microseconds over decades, but measurable. Now imagine the extreme version, near a black hole where gravity twists spacetime like taffy. Time crawls so slowly that an outside observer might see you freeze in place, hovering at the event horizon for what seems like eternity. While for you, seconds pass normally, this cosmic quirk isn't just theoretical, it affects everyday technology. GPS satellites orbit high enough that Earth's gravity weakens slightly, making their onboard clocks tick faster than those on the ground. If engineers ignored this, your phone's navigation would drift off course by nearly 7 miles per day. So satellites deliberately slow their clocks to compensate, a real-world hack bending time's rules. Even stranger, the satellites also move fast enough for special relativity to kick in, which speeds up time slightly. Scientists must balance both effects. Gravity's slow down and motion speed up just to keep your Maps app accurate. The takeaway: time isn't a universal metronome. It's fluid, bending under the weight of planets, stars, and galaxies. A second here isn't the same as a second there, and that's not philosophy. It's physics written into the fabric of the cosmos. If you were to watch an astronaut drift toward a black hole's event horizon, something eerie would happen. From your safe vantage point, their movements would slow, then nearly stop. Their spaceship's clock would tick infinitely slower as they approached that invisible boundary, until time itself seemed to freeze for them. They'd appear to hover there, forever caught in a single moment, like a cosmic fly trapped in amber. But here's the twist: for the astronaut falling in, time passes normally. They'd cross the event horizon without even realizing it, while you'd swear they never quite made it. This bizarre effect comes from general relativity's prediction that gravity doesn't just bend space, it stretches time. Near a black hole, the warping becomes so extreme that light from the falling astronaut takes longer and longer to reach you, redshifting into invisibility. What looks like a freeze frame to you is just reality's version of a buffering video signals from their final moments stretched across eternity. Meanwhile, for them, the universe outside would appear to speed up wildly, like hitting fast forward on cosmic history. Stars might age billions of years in what feels like minutes. The strangest part, neither perspective is wrong. Time isn't absolute, it's relative, shaped by where you are and how you're moving. A black hole's event horizon magnifies this to extremes, creating what physicists call an infinite time dilation zone. It's as if the universe scribbles out the final chapter of the falling astronaut story from our point of view while they experience the full narrative. This paradox reveals time as a pliable dimension, not a universal constant, a fabric that black holes crumple into knots, and if you're wondering what lies beyond that horizon. Even time's arrow might falter there. Some theories suggest the roles of space and time swap places inside a black hole, turning what was once a one-way march into a direction you could stumble through, like walking through walls in a dream. But that's a mystery no signal has ever escaped to confirm. For now, black holes remain the ultimate time-bending enigmas where the universe's clockwork glitches spectacularly. Here's a mind-bending thought. What if, before the Big Bang, is as meaningless a concept as asking what's north of the North Pole? We're hardwired to imagine time as an endless river flowing from past to future. But physics suggests time itself was born in the cataclysm that created our universe 13.8 billion years ago. The Big Bang wasn't just the beginning of matter and energy. It forged the very fabric of space-time, weaving together the dimensions we now take for granted. Before that, there was no before. Without time, there's no framework for events to unfold, no canvas for cause and effect, just an incomprehensible void where even the word void might not apply. Think of it like the edge of a map. Ancient cartographers wrote, "Here be dragons beyond known territories," but the Big Bang is more radical. It's the edge of reality itself. Asking what came before is like a character in a video game wondering what existed before the game's code started running. Time isn't just paused or hidden, the concept simply doesn't compute. Some theories, like loop quantum gravity, suggest spacetime might have been a seething foam of quantum fluctuations, birthing our universe like a bubble in an infinite cosmic froth. Others propose cyclical models where universes rebound from previous collapses, but even then, the idea of before gets slippery, like trying to remember a dream that erased itself. Here's where it gets even stranger. The Big Bang didn't happen at a single point in space. It happened everywhere at once. Picture the universe not as an expanding ball of matter, but as an infinite stretch of spacetime swelling like rising bread dough. Every galaxy, every atom is riding that expansion, carried farther apart by the stretching fabric of reality. And just as dough can't rise without the baker's heat, spacetime couldn't stretch without the unimaginable energy of that initial moment. The afterglow of that energy still whispers to us today as the cosmic microwave background, the oldest light in the universe, frozen in time when atoms first formed. Yet mysteries remain. Why did time choose to flow forward? The laws of physics work just as well if time runs backward, yet we never see shattered teacups reassemble themselves. Some physicists argue the Big Bang set time's arrow in motion by creating a universe with incredibly low entropy, a state of order so improbable that disorder had nowhere to go but up. Others wonder if multiple arrows of time could exist in other universes, or if our perception of time is just a side effect of how our brains process cause and effect. One thing's certain, time's origin story is still being written, buried in the quantum fuzz of the universe's first fractions of a second. So next time you check your watch, remember, you're not just measuring minutes. You're tracing echoes of the universe's explosive birth, counting ticks on a cosmic clock that didn't even exist until reality decided to begin. What if our universe has a mirror image where time flows backward and antimatter versions of us live their lives in reverse? It sounds like science fiction, but the math might actually support it. Enter CPT symmetry, one of physics' most tantalizing ideas. This principle states that if you take any physical process and apply three transformations simultaneously, swapping matter with antimatter C, flipping left and right like a mirror P, and reversing the direction of time T, the laws of physics should hold perfectly. Like a cosmic Sudoku puzzle, the equations balance flawlessly. But here's the kicker. While our universe violates CP symmetry, mirrored antimatter doesn't behave exactly like us. CPT symmetry remains unbroken. That means a universe where all three transformations apply antimatter, mirrored, and time reversed might exist as a perfect shadow to our own. Picture this: somewhere beyond the cosmic horizon, atoms of antimatter assemble into stars that emit light moving backward through time. Galaxies spin in reverse, entropy decreases, and causality itself flips effect preceding cause. You might witness teacups assembling from shattered fragments or flames drawing heat back into logs. For physicists, this isn't just speculation. In 2018, experiments with particles called kaons showed CP violations so precise that CPT symmetry demands a time-reversed counterpart to restore balance. The math insists on it. Why haven't we found this mirror universe? It could be hiding in the cosmic microwave background's anomalies or lurking just outside our observable bubble. Some theories even suggest the Big Bang created twin universes, one moving forward, one backward, like opposing ends of a cosmic hourglass. Others argue that what we perceive as antimatter is that reverse time universe glimpsed fleetingly in particle colliders. The implications are dizzying. If time flows both ways, does free will still hold meaning? Could a reverse time observer watch our Big Bang as their distant future? The answers might lie in the quantum realm, where particles already seem to ignore time's arrow. Until then, CPT symmetry stands as a haunting suggestion that reality's clockwork might tick in both directions, and we're just witnessing half the story. Here's something that turns planetary science on its head. Mercury, the closest planet to the Sun, has a day that drags on longer than its entire year. That's right, if you lived on Mercury, you'd celebrate 2 birthdays before the Sun completed a single journey across your sky. This cosmic quirk happens because Mercury spins at an agonizingly slow pace, trapped in what's called a 3-to-2 spin orbit resonance. For every 2 laps it makes around the Sun, the planet rotates exactly 3 times on its axis. Why this bizarre dance? Blame tidal forces, the same gravitational tug that gives Earth ocean tides. Mercury's proximity to the Sun subjects it to crushing gravitational stress, which over billions of years has sculpted its rotation into this precise rhythm. The Sun's pull creates a kind of cosmic friction, slowing Mercury's spin until it's settled into this stable ratio. It's like a child on a swing, pushing at just the right moment to keep the motion steady. If Mercury spun faster or slower, the Sun's gravity would tug it back into sync, forcing it into this strange celestial metronome. Picture standing on Mercury's scorched surface. The Sun wouldn't rise and set like it does on Earth. Instead, it would crawl across the sky, stall, reverse briefly, then resume its creep, all because Mercury's lopsided orbit combines with its sluggish rotation. At certain points, you could watch the Sun rise, pause overhead, and dip back below the horizon before rising again. A single Mercurian solar day from noon to noon stretches a staggering 176 Earth days, while its year zips by in just 88. This isn't just a planetary oddity, it's a lesson in celestial mechanics. Similar tidal locking happens across the cosmos. Our moon shows Earth only one face, and some exoplanets likely freeze in eternal day or night. But Mercury's 3-to-2 resonance is rarer. a delicate balance between rotation and revolution that reveals how gravity choreographs time itself across the universe. So next time you glance at your watch, remember, out there, timekeeping can get seriously weird. Ever boarded a plane and felt like time moved just a tiny bit slower? It actually does, but not enough for you to notice. According to Einstein's special relativity, the faster you travel through space, the slower time ticks for you compared to someone standing still. Let's break this down with the classic twin paradox. Imagine one twin stays on Earth while the other rockets off at nearly the speed of light. When the traveling twin returns decades later, they'd step off the ship looking noticeably younger than their Earth-bound sibling. Time didn't just feel slower for them, it physically was slower. Their heartbeats, their metabolism, even the atoms in their body experienced fewer ticks of the cosmic clock. This isn't just theoretical. Scientists have proven it with particles called muons, which are created when cosmic rays hit Earth's atmosphere. These particles decay so quickly that, based on their lifespan, they shouldn't even reach the ground. But because they're zipping through the air at close to light speed, time stretches for them like taffy. From our perspective on Earth, their internal clocks slow down just enough to let them survive the journey. It's as if the universe hands them a time bonus for moving fast. Here's where it gets wild. This effect isn't limited to rockets or subatomic particles, it's happening to you right now. Every time you walk, drive, or even fidget in your chair, you're ever so slightly bending time. A clock on a satellite in orbit, moving thousands of miles per hour, ticks measurably faster than one on Earth's surface. Even the speed of a commercial airliner introduces a tiny time difference. Passengers on a long flight age a few nanoseconds less than people on the ground. Special relativity flips our intuition about time as a universal constant. There's no master clock ticking steadily across the cosmos. Instead, each of us carries our own personal version of time, warped by how we move through space. Two events that seem simultaneous to a stationary observer might happen hours apart for someone speeding past. The universe doesn't care which perspective is right. It simply lets motion rewrite the rules of time itself. So next time you're stuck in traffic, remember, you're not just moving through space, you're sculpting time with every turn of the wheel. The present moment feels solid, immediate, but what if it's just a trick of perspective? Physics suggests that what we perceive as now might be no more real than a single frame in an already recorded film. This is the block universe theory, where time isn't a flowing river but a frozen landscape where past, present, and future all exist simultaneously. Think of it like a cosmic DVD. Every scene, your birth, the dinosaurs' reign, the heat death of the universe already exists on the disc. We're just watching one chapter at a time, mistaking the current scene for the only reality. Take the Andromeda Galaxy, our Milky Way's nearest neighbor. When you gaze at its faint smudge in the night sky, you're seeing light that left Andromeda 2.5 million years ago, around the time early humans were crafting stone tools. But here's the twist: the real Andromeda, the version where stars might have exploded or aliens could be building civilizations, exists right now in what we'd call its present. We just can't see it yet because light hasn't had time to reach us. In the block universe, both versions, the one we observe and the one we can't, are equally real, stacked like pages in a book. This challenges everything we assume about time. If the future is already out there, does free will evaporate? Not necessarily. Some physicists argue the block universe simply means all possible states exist, and our choices determine which path we experience. Others compare it to a maze where every turn is predetermined, but you still feel the thrill of discovery. Either way, the theory forces us to confront a bizarre truth. Your childhood, your next birthday, and your final breath might all be equally real in the grand tapestry of spacetime, just separated by coordinates we perceive as time. The implications ripple outward. GPS satellites must account for time dilation, but the block universe suggests they're not just adjusting clocks. they're reconciling different slices of a fixed reality. Even quantum entanglement, where particles instantly influence each other across vast distances, makes more sense if time's flow is an illusion. Perhaps what we call the present is just the narrow slice of the block our brains can process, like ants crawling along a single thread in a vast tapestry. So next time you check the time, remember, your watch isn't tracking the universe's progress. It's highlighting your position in a structure where every moment, from the Big Bang to the last black hole's evaporation, already has its place. The present isn't a point, it's a perspective. Living aboard the International Space Station turns astronauts into accidental time travelers, but not in the way sci-fi suggests. Up there, orbiting Earth at 17,500 miles per hour, while experiencing just 90% of our surface gravity, time literally ticks slower for them. Over a typical 6-month mission, an ISS crew member ages about 0.005 seconds less than those of us planted firmly on the ground. That might sound negligible, but stretch it to a decade in space and the difference grows to nearly 1/10 of a second. This time warp stems from two competing relativistic effects. First, the station's blistering speed, thanks to Einstein's special relativity, slows astronauts' clocks compared to Earth's. But here's the twist, they're also farther from Earth's gravitational grip, which, per general relativity, speeds their time back up slightly. The two effects don't perfectly cancel out. Velocity wins by a hair, making ISS residents age slower overall. It's like racing against a clock while simultaneously being pushed forward on a cosmic treadmill. Consider the precision required to measure this. Atomic clocks aboard GPS satellites already account for similar effects, but the ISS provides a living lab. Scientists track these micro-shifts by comparing ultra-precise clocks on the station with synchronized counterparts on Earth. Even the station's orbit matters. At 250 miles up, gravity weakens just enough to flip the script on deeper space missions. Future Mars travelers experiencing weaker gravity and high speeds would see their clocks drift even more. The implications stretch beyond theory. Prolonged space habitation could create a weird scenario where astronauts return technically younger than peers by trillionths of a second, sure, but proof that time isn't the constant we assume. Imagine generations born in space colonies where accumulated time differences shift their place in Earth's historical timeline. A family living off-world for centuries might lag minutes behind, their personal now subtly out of sync with the planet they left. This cosmic quirk forces us to rethink aging itself. Biological clocks, cell division, metabolism, all bow to spacetime's rules. If humanity becomes multiplanetary, we might need flexible calendars accounting for orbital speeds and planetary gravity. Your space age could differ from your Earth age, like interplanetary daylight savings time. For now, astronauts shaved off microseconds are a curiosity. But they're also a reminder, time's flow isn't dictated by clocks. It's negotiated by motion and gravity, a fluid dance across the universe. Quantum mechanics has a habit of turning common sense inside out, but nothing shatters our intuition about time quite like the delayed choice quantum eraser experiment. Imagine firing a particle of light, a photon, toward a screen through a special setup that forces it to behave either as a particle or a wave. Here's where things get bizarre. The photon appears to decide whether it traveled as one or the other after it's already been detected, as if rewriting its own history based on future observations. It's not just acting randomly, it's responding to measurements we haven't even made yet. This phenomenon, called quantum retrocausality, suggests that particles might not just experience time differently, they might bend it backward. Picture tossing a tennis ball against a wall, only for the ball to change its trajectory before your racket makes contact. That's essentially what happens at the quantum level. In one famous variation of the experiment, scientists split photons into entangled pairs, sending one half to a detector while delaying the measurement choice for the other. The mind-blowing result: The first photon's behavior depended on how its entangled partner was later observed, even though that observation occurred nanoseconds after the initial detection. Critics argue this isn't true time travel but a quirk of probability waves collapsing across time. Yet the implications are staggering. If quantum events can be influenced retroactively, it challenges the bedrock idea that causes must precede effects. Some interpretations propose that at the smallest scales, time might loop like a Möbius strip, with future and past constantly negotiating each other's boundaries. Others speculate that entanglement creates a kind of temporal bridge where particles share information outside linear time altogether. What makes this more than a lab curiosity is how it echoes in the larger universe. Black holes, with their extreme warping of spacetime, might amplify these effects. Could entangled particles falling into a singularity send ripples backward through time? The math doesn't rule it out. Even our own biology might whisper hints. Some theories suggest quantum processes in photosynthesis or bird navigation exploit subtle time-bending effects. The takeaway: time's arrow might not be a one-way street in the quantum realm. Particles could be threading the needle of causality in ways we're only beginning to glimpse, rewriting history at the smallest scales, one photon at a time. Broken eggs don't unscramble themselves, coffee never unstirs from your cup, and you'll never meet a 70-year-old who grows younger each birthday. These everyday impossibilities trace back to one of physics' deepest mysteries: why time only flows forward. The answer lies in entropy, a concept so fundamental that it dictates the arrow of time itself. Picture entropy as nature's relentless mess maker. It measures how disordered a system is, and the universe has an ironclad rule: entropy always increases. Once an egg shatters, its molecules tumble into countless disordered states. For them to spontaneously regroup into a pristine egg would be like expecting a tornado to assemble a house from scattered debris. Here's where it gets profound. The laws of physics don't actually forbid time from running backward. Equations for gravity or quantum mechanics work just as well in reverse. But entropy throws a wrench in the works. At the Big Bang, the universe began in an improbably low entropy state, like a perfectly stacked deck of cards. Ever since, it's been shuffling itself toward chaos, creating the one-way street we perceive as time's flow. This is why we remember the past but not the future. One direction has the orderly records like footprints in sand, while the other is a storm of randomness. Think of a drop of ink swirling in water. The moment it disperses, trillions of molecules explore countless configurations. For them to spontaneously regroup into a droplet would require navigating an astronomically improbable path, like winning the lottery billions of times in a row. Yet at the quantum level, particles occasionally pull off such feats. This tension between thermodynamics' rigid arrow and quantum mechanics' playful time symmetry fuels debates about whether time's direction is fundamental or just a statistical fluke of our cosmic starting point. Some theorize other universes might have arrows pointing backward or even branching in multiple directions. Others suggest entropy's rise might one day reverse if the universe collapses in a big crunch, resetting time's arrow like a flipped hourglass. For now, we're stuck with the reality that broken eggs stay broken, and that's why yesterday feels different from tomorrow. We think of time as an unbroken river, flowing seamlessly from one instant to the next, but what if it's more like a flipbook flickering through tiny, indivisible frames? At the unfathomably small scale of the Planck length, about 10 to the power of -43 seconds, some physicists suspect time might not be continuous at all. Instead, it could be made of discrete chronons, the smallest possible units of time, like pixels on a cosmic screen. This idea shakes the foundations of how we perceive reality, suggesting the universe operates in quantum ticks rather than a smooth stream. Imagine watching a movie where each frame is separated by a tiny gap. Your brain stitches them into fluid motion, but the underlying reality is a series of snapshots. If time is granular, our experience of continuity could be just as illusory, a trick played by consciousness on a universe that fundamentally renders existence in finite steps. The Planck scale is so absurdly small that a single chronon lasts a millionth of a trillionth of a trillionth of a trillionth of a second. At that resolution, even the fastest physical processes would unfold in measurable jumps, like a clock whose hands move in invisible clicks. Why does this matter? For starters, a pixelated timeline could resolve paradoxes in quantum mechanics. Particles pop in and out of existence seemingly at random, but if time itself advances in discrete packets, their behavior might follow rules we can't yet see. It's like discovering that a random light show is actually synced to a strobe light too rapid for our eyes to detect. Some theories, like loop quantum gravity, propose spacetime itself is woven from these elementary threads with chronons acting as the stitches. The implications ripple outward. If time is granular, there might be a cosmic frame rate, a limit to how quickly any change can occur. Just as a video game lags if too much happens between refreshes, the universe could have a maximum processing speed. Events unfolding faster than one Planck time wouldn't just be unobservable, they'd be physically impossible. This could cap everything from particle interactions to the very speed of thought. Even black holes, those notorious spacetime shredders, might hit a limit when trying to process infalling matter beyond the chronon threshold. Critics argue we'll never detect such fleeting intervals directly. Current technology can't probe timescales that brief. But indirect clues might lurk in high-energy cosmic rays or the faint echoes of the Big Bang. If chronons exist, they'd imprint subtle jitters on particles moving near light speed, like a bike bouncing over cobblestones too fine to see. Others suggest granular time could explain why quantum particles seem to teleport. They're not moving smoothly but hopping between chronons like a character glitching between video game frames. The wildest possibility, a granular universe might not even have a now in the way we experience it. If time advances in Planck-sized steps, all changes across the cosmos could sync to these universal ticks, like pixels lighting up in unison on a cosmic display. Your perception of the present might just be your brain's way of interpreting the latest frame in a reality that refreshes faster than thought itself. So next time you check your watch, consider this. Those ticking seconds might be the coarsest approximation of a far stranger truth. That time, at its heart, isn't a flow but a staccato rhythm, playing out in quantum whispers too faint for even atoms to hear. Gaze up at the night sky, and you're not just seeing stars, you're peering into a cosmic graveyard. Many of those twinkling points of light burned out millions of years before their final photons reached your eyes. The light from even our closest stellar neighbor, Proxima Centauri, takes over 4 years to arrive, meaning you're seeing it not as it is today, but as it existed when that light began its journey. Now imagine amplifying that effect across the vastness of space. The Hubble Ultra Deep Field, one of humanity's most profound cosmic snapshots, captures galaxies so distant their light has traveled for over 13 billion years. By the time these photons touched Hubble's mirror, some of those majestic spirals and ellipticals might have already collided, faded, or collapsed into supermassive black holes. This celestial time machine effect reveals something astonishing. When we observe distant galaxies, we're not just looking across space, we're looking backward through time. The farther out we peer, the younger the universe appears. The ultra-deep field shows galaxies as they were just 400 million years after the Big Bang, infants by cosmic standards, their stars blazing with primordial intensity. Some of these early galaxies emitted their last light 12 billion years ago, yet their final whispers are only now reaching us like letters from a long-dead pen pal finally arriving in your mailbox. Here's where astronomy becomes detective work. When we analyze light from these ancient stars, we're decoding chemical fingerprints from the universe's childhood, a time when heavy elements like gold and uranium barely existed. The absence of certain elements in their spectra tells us these stars belong to generations that lived fast and died young, seeding the cosmos with the raw materials for planets and life. And some of the dimmest red dwarfs spotted in these deep fields could still be burning today, having outlasted entire galactic eras while their light took eons to cross the void. The ultimate twist: if intelligent life exists in those faraway galaxies, and if they possessed telescopes powerful enough to see us, they wouldn't witness bustling cities or satellite-laden skies. They'd see an Earth untouched by civilization, a world where continents were still drifting into their modern configurations. The cosmic speed limit of light creates a universe where every observation is a historical document, and every telescope is fundamentally an archaeological tool. So next time you stare at the stars, remember, you're not just seeing points in space, you're witnessing chapters from the universe's biography, written in photons that outlived the very objects they came from. The night sky is less a map than a mosaic of epitaphs, and we're only beginning to read them. During the Apollo 10 mission, a final dress rehearsal before landing on the moon, an unexpected timekeeping glitch almost scrambled history. As the spacecraft hurtled back to Earth at nearly 25,000 miles per hour, its onboard clock began subtly disagreeing with Mission Control's time-stamped communications. The discrepancy, just 36 microseconds, a blink too brief for humans to notice, but enough to throw off critical navigation calculations. This tiny hiccup wasn't a mechanical error. It was Einstein's theory of relativity playing out in real time. Here's what happened. According to special relativity, the faster you move through space, the slower your clock ticks compared to someone at rest. For Apollo 10, racing home at 7% the speed of light, this meant time aboard the spacecraft dilated ever so slightly. Meanwhile, general relativity added another layer. Earth's gravity tugs harder on Houston's ground-based clocks than on the spacecraft's, speeding them up by an opposing fraction. Normally, these effects cancel out for satellites in stable orbits, but Apollo 10 wild velocity swings during re-entry amplified the mismatch. Engineers suddenly faced a scenario where the spacecraft's perception of time no longer aligned with Earth's, like two musicians playing the same symphony at imperceptibly different tempos. NASA had anticipated this. Even in the 1960s, physicists knew relativity would affect space travel. Mission planners baked corrections into the software, nudging Apollo 10 clock to stay in sync. Without these adjustments, the tiny time discrepancy would have snowballed, potentially skewing trajectory computations by meters, enough to endanger splashdown precision. Modern GPS satellites face this daily, compensating for time dilation by intentionally slowing their atomic clocks before launch. But Apollo 10 marked one of the first times relativity's ghost had to be reckoned with mid-mission, proving Einstein's math wasn't just abstract theory. It was the difference between a triumphant return and a wayward capsule. The wildest part, this same effect could reshape future deep space travel. A crewed mission to Mars, moving faster and farther than Apollo, might accumulate milliseconds of clock drift enough to require real-time relativistic corrections. Imagine astronauts syncing their watches not just with Earth, but with the warped spacetime of interplanetary flight. Apollo 10 microsecond hiccup was a whisper from the universe, reminding us that even humanity's boldest leaps still dance to the rhythm of spacetime's flexible rules. So the next time you check the clock, remember, timekeeping isn't just engineering. It's a negotiation with the cosmos, one where speed and gravity always get the final say. Here's something that'll make you rethink your morning height measurement. Your head is technically aging faster than your feet. Not by much, of course, but according to Einstein's general relativity, time ticks slower the closer you are to a massive object like Earth. Since gravity weakens with distance, the few feet separating your head from your toes create a tiny but real-time dilation effect. For someone 6 feet tall, the difference amounts to about 90 nanoseconds over a 70-year lifespan. That's 90 billionths of a second, roughly the time it takes light to travel 30 meters. Not enough to notice, but enough for physics to confirm. Standing up literally buys you more time. Why does this happen? Imagine space-time as a stretched rubber sheet with Earth pressing down in the center. The deeper the dent, the slower time flows, so your feet, being slightly closer to the planet's core, sit in a slightly deeper gravity well than your head. It's like living in a very gentle version of the time warp near a black hole. Atomic clocks are precise enough to measure this effect. In one famous experiment, scientists placed one clock at sea level and another on a table just a foot higher. Over a day, the elevated clock ticked a few trillionths of a second faster, exactly as relativity predicts. The implications get wilder beyond Earth. On a neutron star, where gravity is billions of times stronger, an astronaut's head would age years faster than their feet over a short visit. Even GPS satellites have to account for this. Their altitude means their clocks tick faster than ground-based ones, but their orbital speed counteracts some of that. Without these corrections, your phone's navigation would fail within minutes. So while you won't feel your brain gaining nanoseconds on your toes, this effect is a quiet reminder that gravity doesn't just hold us down, it sculpts time itself, one atomic vibration at a time. What if time isn't a fundamental part of the universe, but more like temperature, an emergent property that arises from something deeper? This radical idea comes from quantum physics, where researchers are piecing together clues that time might not be woven into the fabric of reality at its most basic level. Instead, it could be a side effect, like the way wetness emerges from countless water molecules interacting, even though no single molecule is wet. At the heart of this theory is quantum entanglement, the bizarre phenomenon where particles become linked across vast distances, instantly influencing each other no matter how far apart they are. Some physicists, like those working on the thermal time hypothesis, suggest that what we experience as the flow of time could actually be a kind of quantum ledger, tracking how entangled states evolve across the universe. Picture a cosmic game of dominoes. Each quantum interaction topples the next, creating the illusion of a sequence, our perception of past, present, and future. Even stranger is the concept of timeless physics. In certain quantum gravity models, the fundamental equations don't include time as a variable at all. It's like describing a movie solely by its frames without needing a timestamp. Time emerges only when we zoom out, much like how the smooth motion of a film arises from static images flashing rapidly. Experiments with tiny quantum systems already hint at this. When particles are deeply entangled, their interactions can define a kind of local time, even if no universal clock exists. This challenges everything from cosmology to consciousness. If time is emergent, the Big Bang might not be the beginning of time, but the moment it crystallized from a more primal state. Our brains, evolved to track cause and effect, could be mistaking this quantum choreography for a flowing river. The present moment might feel real, but it could just be the universe's way of making sense of itself, one entangled interaction at a time. Right now, countless galaxies are vanishing from our cosmic view, not because they're disappearing, but because the universe itself is stretching space faster than light can cross it. This accelerating expansion, discovered in 1998 through observations of distant supernova, creates an eerie effect, regions of space so far away that their light will never reach us. These galaxies aren't just far, they're slipping behind a cosmic event horizon, where their version of now becomes permanently unknowable to us, like ships disappearing over the edge of an expanding ocean. Think of space as an infinite loaf of raisin bread baking in the oven. As the dough expands, raisins' galaxies move apart. But if the loaf rises fast enough, some raisins will recede so quickly that light from them can never reach others, no matter how long you wait. This isn't a matter of telescope power or patience. It's a fundamental limit set by dark energy, the mysterious force behind the acceleration. Even if we built a time machine to wait trillions of years, those regions would remain blank spots in our sky, their stars and planets frozen in our observations as they were when their final photons crossed the horizon. What makes this unsettling is that we're not just losing touch with distant galaxies, we're losing entire epochs of cosmic history. The universe's expansion rate suggests that today, about 97% of all observable galaxies lie beyond this horizon. Their current state, whether they've birthed new civilizations or collapsed into black holes, is information we'll never access. We see only their ancient light like postcards from a receding shore. The implications twist our understanding of now. If aliens in one of those vanishing galaxies aimed telescopes at Earth today, they wouldn't see cities or satellites, they'd see a planet before multicellular life arose if they saw Earth at all. Meanwhile, our descendants billions of years from now will peer into a far emptier night sky, with most galaxies redshifted into invisibility. The universe's accelerating expansion means that time isn't just a river carrying us forward. It's also erasing entire chapters of reality from our view, sealing them away like pages in a book we can no longer open. This cosmic censorship forces us to confront a humbling truth. Not only is the universe vaster than we can observe, but its full story is fundamentally unknowable. Future astronomers might detect only our local galactic cluster, unaware of the immensity beyond. The present isn't a universal moment, it's a local bubble shrinking as space stretches faster. Even as we map the cosmic microwave background, that afterglow of the Big Bang, we're stuck studying fossils of a universe whose living body is mostly already beyond our reach. Yet there's a strange beauty in this. Just as ancient humans told stories by campfires under starry skies we now know are mostly gone, we too are time travelers peering not just across space, but into a past where the universe was smaller, slower, and still within reach. The light arriving tonight from distant quasars might be the last we'll ever receive from them, like final messages in cosmic bottles washing ashore before the tide goes out forever. In a universe where everything from planets to particles eventually slows down and stops, there exists a bizarre form of matter that defies one of time's most fundamental rules: time crystals. Unlike any ordinary crystal, which has atoms arranged in repeating patterns in space, time crystals exhibit structure in time, oscillating between states without absorbing or losing energy. Imagine a pendulum that swings forever without any push, a clock that ticks without winding, or a diamond that spontaneously changes its atomic arrangement every few seconds like an eternal dance. This isn't perpetual motion, it's a quantum loophole where order emerges from the fabric of reality itself. The existence of time crystals was first proposed in 2012 by Nobel laureate Frank Wilczek, but many physicists dismissed the idea as impossible. How could something cycle indefinitely without violating the laws of thermodynamics, which demand energy loss? The breakthrough came in 2017 when two separate teams, one using chains of ytterbium atoms, the other a diamond riddled with nitrogen impurities, created time crystals in the lab. These systems didn't magically generate energy. Instead, they exploited quantum entanglement to lock into a rhythm, flipping between configurations in a fixed loop. It's like a group of synchronized swimmers who keep perfect timing without ever checking the clock, their movements locked into place by an invisible quantum choreography. What makes time crystals so revolutionary is how they shatter time translation symmetry, the assumption that physical laws work the same at every moment. A time crystal doesn't care if it's Monday or a billion years from now. It ticks with the same regularity, immune to external chaos. In experiments, researchers blasted the systems with laser pulses to wind them up, but instead of responding immediately, the crystals oscillated at a slower, intrinsic pace, like a metronome stubbornly keeping its own beat. This behavior hints at a new phase of matter, one where time itself becomes a playground for quantum weirdness. Practical applications are still speculative, but the implications are staggering. Time crystals could lead to fault-tolerant quantum computers, where information is stored in their unshakable rhythms rather than fragile qubits. Some theories even suggest they might help simulate exotic physics, like wormholes or the early universe's conditions. For now, they stand as a reminder that time, far from being a featureless backdrop, might harbor structures as intricate as the most complex crystal. The universe's clockwork just got a lot stranger, and we're only beginning to hear its ticks. Venus, Earth's so-called twin, hides a cosmic absurdity beneath its thick clouds, a day so sluggish it outlasts an entire trip around the Sun. While the planet zips through its orbit in just 225 Earth days, it takes a glacial 243 Earth days to complete a single rotation on its axis. That means if you lived on Venus, a sunrise-to-sunrise cycle would stretch longer than the planet's entire year. To make things even weirder, Venus spins backward compared to nearly every other planet in the solar system, a phenomenon called retrograde rotation. Picture a clock running counterclockwise while also moving at the pace of drying paint. Scientists suspect this bizarre rotation stems from a cataclysmic collision in Venus's early history, a planetary smash-up so violent it flipped the planet upside down or dramatically slowed its spin. Alternatively, gravitational tugs from the Sun and Venus's dense, hurricane-speed atmosphere might have gradually braked its rotation over billions of years, like a cosmic hand pressing against a spinning top. The result is a world where timekeeping defies intuition. A Venusian day, one full rotation, lasts longer than its year, one orbit, but because the planet spins backward, the Sun rises in the west and sets in the east, assuming you could even see it through the planet's perpetual sulfuric acid clouds. The practical effects are surreal. If you stood on Venus's surface, which, granted, would cook you at 900 degrees Fahrenheit, you'd experience sunlight for about 116 Earth days straight, followed by an equally grueling stretch of darkness. The planet's atmosphere, thick enough to crush bones in seconds, also exerts such friction that it may be further slowing the rotation, like a spoon dragging through molasses. Some models suggest Venus's day lengthens by about 1 Earth minute every few decades, meaning future probes might land to find a slightly different sunrise schedule than their predecessors recorded. This oddball rotation also means Venus has no true seasons. Earth's tilt creates our summers and winters, but Venus stands almost perfectly upright, its backward spin leaving it with barely any axial tilt at all. Combined with its suffocating blanket of carbon dioxide, the planet's sluggish spin helps create a greenhouse effect gone rogue, making it the hottest world in the solar system despite Mercury being closer to the Sun. So why does this matter? Venus's weird clockwork offers clues about how chaotic planetary formation really is. Most planets spin prograde, aligning with their orbits like marbles rolling around a bowl. Venus's defiance hints at the violence of the early solar system, where collisions and gravitational chaos could flip worlds or slam the brakes on their rotation. It's a reminder that what we consider normal in our cosmic neighborhood might just be a fluke, and that time, even on planetary scales, is anything but uniform. Remember those endless childhood summers that seemed to stretch for years? That wasn't just nostalgia playing tricks on you. Time actually feels slower when you're young. Science suggests our perception of time is like a cosmic rubber band, stretching and compressing based on how our brains process life's moments. One leading theory, called the proportionality hypothesis, argues that as we age, each year becomes a smaller fraction of our total lived experience. At 5 years old, one summer vacation represents nearly 5% of your entire existence, and eternity by comparison. By age 50, those same 3 months shrink to 0.5% of your life, passing in what feels like a blink. But there's more to it than just math. Neuroscience reveals that time perception is deeply tied to novelty and metabolism. Children's brains are like sponges, constantly absorbing new information: first bike ride, first snowfall, first crush. Each fresh experience etches vivid memories, creating a dense mental timeline that makes time feel elongated in hindsight. Adults, meanwhile, often settle into routines. The daily commute, the familiar work tasks, the repetitive rituals, these merge into a cognitive blur, making weeks evaporate. Studies show that when we encounter novel stimuli, our brains churn through more mental frames per second, recording richer details that stretch subjective time. It's why a vacation packed with new sights feels longer when recalled, while months of routine vanish from memory. Here's where biology throws a curveball. Metabolic rate, the speed at which our bodies burn energy, also warps time perception. Children's hearts beat faster, their neurons fire more rapidly, and their internal clocks tick at a different rhythm. Think of it like comparing a hummingbird's wing beats to an eagle's. Some researchers speculate that this metabolic intensity makes kids process more moments per minute, creating a slower motion effect. Animal studies support this. Mice with higher metabolisms react to stimuli as if time is dragging, while sluggish turtles seem to experience it as flying by. The creepiest part, trauma can hijack this system. During life-threatening events, adrenaline floods the brain, hyper-activating memory formation. That's why car crashes or falls often unfold in surreal slow motion. Your brain crams extra snapshots into a few seconds, stretching subjective time like taffy. But this isn't time dilation a la Einstein. It's your biology weaponizing perception for survival. So while physicists measure time with atomic clocks, our lived experience is sculpted by memory, novelty, and the quiet ticking of cellular engines. Those endless childhood summers weren't an illusion. They were the product of a brain marinating in wonder, stitching together a timeline so dense with firsts that it could never be replicated. The irony, the older we get, the faster time seems to slip away precisely because we've stopped paying attention. Slow down, embrace novelty, and maybe, just maybe, you'll stretch time's elusive fabric once more. Here's something that sounds like a cosmic prank. The universe isn't just expanding, it's stretching space so fast that time itself is speeding up in the most distant reaches of reality. This mind-bending twist comes courtesy of dark energy, the mysterious force pushing galaxies apart at an ever-increasing rate. Here's how it works. As the space between galaxies widens, light from those distant regions has to traverse more and more stretched-out spacetime to reach us. That journey doesn't just redshift the light, it slows down the appearance of time in those faraway places from our perspective. But here's the paradox. For hypothetical observers in those distant galaxies, time feels normal, while our corner of the universe would seem to be moving in fast forward. Picture a cosmic funhouse mirror where reflection delays warp your movements. If you waved at a mirror a light year away, your reflection would take a year to respond. Now imagine the mirror itself is racing backward at nearly light speed. Your reflection's movements would crawl, stretching seconds into years. That's essentially what's happening across the universe. As galaxies flee beyond our cosmic horizon, their light struggles to keep up with the stretching space, making their clocks appear to tick slower to us. But flip the viewpoint. If aliens in one of those galaxies trained telescopes on Earth, they'd see our civilizations flicker like time-lapse photography, with centuries passing in what feels like moments. This illusion isn't just theoretical. Astronomers observe it in the light from supernova exploding stars in distant galaxies. Their light curves, which should follow a predictable brightening and fading sequence, appear stretched out as if time itself is dragging in those faraway locales. But the real kicker, this effect grows stronger as dark energy accelerates the expansion. Billions of years from now, any remaining civilizations might peer into the sky and find most of the universe frozen in a single moment, its light redshifted into oblivion. The cosmos won't just be expanding, it'll be erasing entire epochs from view, like pages torn from a history book faster than they can be read. What does this mean for time's arrow? If you could live long enough, you'd witness the universe's timeline fracture into islands of causality, each region ticking to its own isolated rhythm. Galaxies already invisible to us today might have birthed and lost civilizations in what we'd perceive as an instant. Meanwhile, our own Milky Way's future stars dying, black holes evaporating, would unfold in a blink for those distant observers. Time, already relative, becomes a hall of mirrors at cosmic scales, where now splinters into countless fractured perspectives. This isn't just a curiosity, it reshapes how we understand the universe's fate. If distant time appears to slow from our vantage point, does that mean the heat death of the universe happens later in those regions? Or is it all an illusion, a trick of light struggling across an ever-widening gulf? The answers might lie in the quantum foam of spacetime itself, where dark energy's relentless push could be weaving time's tapestry into ever stranger patterns. One thing's certain, the universe isn't just running out the clock, it's rewriting time's rules with every accelerating moment. Some black holes don't just sit ominously in space, they spin with such ferocious speed that they twist the very fabric of reality around them. These cosmic whirlpools, known as Kerr black holes after mathematician Roy Kerr, who first solved Einstein's equations for rotating black holes, can reach speeds approaching light itself. Their rotation is so violent that it doesn't just bend space-time, it drags it like taffy, creating a swirling vortex where even light struggles to resist being pulled along for the ride. The most extreme effects happen near the black hole's ergosphere, a football-shaped region just outside the event horizon where space-time is whipped into a frenzy. Here, the spin is so overpowering that nothing, not even particles or light, can remain stationary. The laws of physics force everything to rotate with the black hole, like leaves caught in a hurricane. Astronomers call this phenomenon frame dragging, and it's so intense near a Kerr black hole that time itself warps unpredictably. An observer watching from a safe distance would see clocks near the ergosphere slow to a crawl, then speed up erratically, as if reality itself were glitching. What makes these spinning monsters even stranger is their potential to become cosmic time machines, at least in theory. Calculations suggest that if you could survive a trip into the ergosphere of a Kerr black hole, you might emerge in a different point in time. The swirling spacetime could create closed time-like curves, loops where the future bends back to meet the past. Picture throwing a ball into a whirlpool and watching it circle back to you from the opposite direction, except instead of a ball, it's your own timeline folding in on itself. Of course, the tidal forces would shred any known material long before this became practical, but the math insists it's possible. The real-world evidence for these spinning black holes is mounting. When the Event Horizon Telescope captured the first image of a black hole's shadow in Messier 87, subtle asymmetries in its ring of light hinted at rapid rotation. Later observations of jets blasting from galaxies like Cygnus X1 revealed black holes spinning at over 90% the speed of light, their ergospheres acting like particle accelerators that launch matter across cosmic distances. Yet the ultimate Kerr black hole remains hypothetical, the naked singularity. If a black hole spins fast enough, some models suggest the event horizon could vanish, exposing the singularity to the outside universe. Without the horizon's protection, the laws of physics as we know them might unravel, leaving a rogue knot of infinite density spinning in plain sight. Thankfully, no confirmed naked singularities exist, but if they did, they'd rewrite our understanding of causality, time, and the limits of reality itself. For now, Kerr black holes stand as both a testament to Einstein's genius and a reminder that the universe has no obligation to make intuitive sense. Their existence proves space-time isn't just a stage, it's a dynamic, twistable medium that even the mightiest objects in existence can't resist bending to their will. We've always thought of time as a single, one-way street, but what if it's more like a sprawling intersection, with multiple dimensions branching in directions we can't perceive? Some physicists speculate that our universe might have not just one, but two or more dimensions of time, a concept that could untangle some of quantum mechanics' strangest puzzles. Imagine living in a world where your timeline isn't just a straight path from birth to death, but a web where moments split and reconnect like threads in a tapestry. This radical idea arises from the math behind certain unified theories, like M-theory in string theory, which requires extra dimensions to make the equations work. While most discussions focus on spatial dimensions, a handful of models suggest adding a second time dimension could resolve inconsistencies in quantum mechanics, particularly the measurement problem, where particles seem to exist in multiple states until observed. With an extra time dimension, quantum superpositions might not collapse into a single outcome, but instead branch along different temporal axes like a train switching tracks. Causality wouldn't break, it would simply become more complex, with events influencing each other across multiple timelines. Think of it like this: in our everyday experience, time is a river flowing in one direction. But with two time dimensions, it becomes a delta, a network of channels where the flow splits and merges. A particle could appear to be in two places at once because it's moving along separate temporal paths, like a traveler hopping between parallel streams. Some theories even propose that dark matter, the invisible glue holding galaxies together, could be ordinary matter moving along a second time dimension, forever out of sync with our own. The implications rewrite physics rulebook: quantum entanglement, where particles instantly influence each other across space, might not require spooky action at a distance. Instead, entangled particles could be connected through higher time dimensions, bypassing our linear causality. Black holes, already notorious for warping space-time, might gateways where these extra-temporal dimensions become tangible. Even consciousness gets a twist. Our perception of time's flow could be a shadow of deeper, multidimensional processes. Skeptics argue that extra time dimensions would destabilize reality, allowing paradoxes where effects precede causes. Yet proponents counter that the laws of physics could enforce a kind of causal harmony, preventing contradictions by weaving events into a stable, if knottier, fabric. Experiments to test this are far beyond current technology, but some researchers suggest subtle signatures might lurk in high-energy particle collisions or the cosmic microwave background's faint irregularities. Whether real or not, the idea challenges us to rethink time's nature. If multiple time dimensions exist, our universe isn't just a cosmic movie playing forward. It's an infinite library of films, each frame branching into alternate reels. The arrow of time might be just one thread in a vast temporal tapestry, and our perception of now merely a slice through dimensions we're only beginning to imagine. Every time you glance at your hand, you're not seeing it as it is. You're peering roughly 3 nanoseconds into the past. That's how long light takes to bounce off your skin and hit your retina. It's an imperceptible delay, but it reveals a profound truth. Vision is always hindsight. The world you perceive isn't the present, it's a mosaic of moments already gone, stitched together by your brain into what feels like now. Scale this up to astronomical distances and the effect becomes staggering. The sunlight warming your face, it left the sun's roiling surface 8 minutes and 20 seconds ago. If our star suddenly vanished, you'd keep basking in its glow for those precious minutes, blissfully unaware you were orbiting a ghost. Peer at Jupiter through a telescope, and you're seeing the gas giant as it was 30 to 50 minutes earlier, enough time for storms to erupt or moons to shift position before your eyes could register the change. Now consider the Andromeda Galaxy, that hazy smudge 2.5 million light-years away. The photons hitting your retina tonight began their journey when early humans were mastering stone tools. Every star in that spiral is a fossil image, their current states forever hidden until their light crawls across the cosmic void. Astronomers study galaxies so distant we see them as they were just 400 million years after the Big Bang, a snapshot of cosmic infancy. By now, those galaxies may have collided, birthed civilizations, or evaporated into black holes. We'll never know. This time lag transforms astronomy into a kind of archaeology. When the James Webb Space Telescope captures infrared light from the earliest galaxies, it's not just collecting photons, it's gathering echoes from an era when the universe was a toddler, still learning to walk. Even mundane observations carry history. A supernova witnessed in 1054 by Chinese astronomers left behind the Crab Nebula, but its light reached Earth centuries after the actual explosion. We're cosmic historians piecing together stories from delayed dispatches. The creepiest implication: if aliens in Andromeda pointed telescopes at Earth right now, they'd see woolly mammoths roaming the plain. Our radio signals haven't even traveled 1% of the way to them. The universe's strict speed limit for information creates a fragmented reality where now is local and always slightly out of reach. Your reflection in a mirror 1 light-year away would show you as you were a year ago, a time capsule hovering in space. This isn't just trivia, it rewrites how we understand observation. Every glance at the night sky is a glimpse into layered histories, with nearer objects like the Moon 1.3 light-seconds away superimposed over ancient galaxies. Your eyes become time machines, their viewfinder dialed to different epochs. Even your smartphone screen displays images nanoseconds old, making our entire visual existence a carefully orchestrated illusion of recency. So next time you watch a sunset, remember, you're not just seeing light, you're catching the universe's oldest messages stamped with expiration dates from the past. Time travel to the future isn't science fiction, it's happening right now, and you might have already met someone who's done it. Every returning astronaut steps off their spacecraft ever so slightly younger than if they'd stayed on Earth. Take Scott Kelly, who spent 340 days aboard the International Space Station. Thanks to his blistering orbital speed of 17,500 miles per hour combined with Earth's weaker gravity at that altitude, he aged about 8.6 milliseconds less than his twin brother Mark back on the ground. That's a microscopic difference, but it proves Einstein was right. Motion literally lets you outrun time. This effect, called time dilation, scales dramatically with speed. Imagine boarding a futuristic spaceship that accelerates to 99.9% of light speed. After a 5-year round trip to a nearby star, you'd return to find Earth decades older while you'd barely aged. The math is airtight. Special relativity guarantees it. We've even measured this with subatomic particles. Muons created in Earth's atmosphere should decay before reaching the ground, but their near-light speed velocity stretches their lifespans, letting them time travel fractions of a second into our future. The real kicker: this isn't some exotic physics trick. Time dilation subtly influences everyday technology. Your GPS receiver depends on satellites whose atomic clocks run faster than Earth-bound ones by about 38 microseconds per day. Without adjusting for both their orbital speed, which slows time, and higher altitude, which speeds it up, your phone's navigation would fail within minutes. Engineers essentially programmed relativity into the system, making it one of the few consumer technologies that literally bends time to work. So why don't we notice time warping in daily life? The speeds we encounter are too sluggish to matter. A commercial airliner's velocity buys passengers just a few nanoseconds over a transatlantic flight, less time than it takes neurons to fire. But the principle remains: every time you move, you're choosing a slightly different timeline than someone standing still. The faster you go, the farther into everyone else's future you'll leap. This raises wild possibilities. A civilization mastering near-light speed travel could witness cosmic events in fast forward. Imagine astronauts departing today and returning in Earth year 3000, having experienced only a subjective decade. Their bodies, clocks, and even relationships would be out of sync with the world they left. True time travelers, not through magic, but through physics. The universe doesn't just permit future hops, it demands them whenever something moves fast enough. Your wristwatch isn't just counting seconds, it's tracking your personal drift through spacetime's elastic fabric. The moon isn't just Earth's celestial companion, it's a pristine museum, frozen in time, holding clues to the solar system's most violent era. Unlike our dynamic planet, where wind, water, and tectonic activity constantly reshape the surface, the moon has no atmosphere, no weathering, no erosion. Every crater, every boulder, every footprint left by Apollo astronauts remains virtually unchanged for billions of years. It's as if the cosmos pressed pause on lunar geology the moment its volcanic fires cooled, turning the entire landscape into a time capsule of celestial violence. Take a closer look at those pockmarked plains through a telescope. What you're seeing isn't just random scarring, it's a meticulously preserved record of the late heavy bombardment, a period around 4 billion years ago when the inner solar system was a shooting gallery. Asteroids and comets rained down in such numbers that Earth's early crust was likely pulverized beyond recognition. But on the moon, those ancient impact scars remain untouched, like bullet holes in a cosmic crime scene. The largest basins, like Imbrium and Oriental, tell stories of planetesimals the size of small countries slamming into the surface with enough force to send shockwaves across the entire moon. This makes lunar craters more than just pits they're history books written in geology. By studying their sizes, depths, and overlapping patterns, scientists can reconstruct timelines of cosmic collisions. The darker patches, or maria, are actually lava flows that seeped into the largest impacts after the bombardment, meaning any craters superimposed on top must be younger. It's like finding a fossilized footprint filled with sediment. The layers reveal the sequence of events. Even the regolith, that fine gray dust covering the surface, holds secrets. Solar wind particles have been embedding themselves in it for eons, creating a record of the sun's activity older than any earthly rock. The moon's archival role goes deeper. Some craters near the poles, forever shadowed from sunlight, are cold traps containing ice deposits that could date back to the solar system's infancy. Comets delivering water to early Earth might have left identical fingerprints here, frozen in time. And because the moon has no plate tectonics to recycle its crust, samples brought back by Apollo missions contain minerals unaltered since their formation. Zircon crystals in lunar rocks have been dated to 4.51 billion years, just 60 million years after the solar system itself coalesced. What's astonishing is how recent some of this history feels. The crater Tycho, with its brilliant rays stretching halfway across the moon, formed a mere 108 million years ago. Dinosaurs were walking Earth when that impact struck. Yet because nothing erases evidence on the moon, Tycho looks as fresh as if it happened yesterday. Compare that to Earth, where erosion would have smoothed such a crater to nothing in a fraction of that time. This pristine record isn't just academic, it's practical. By calibrating impact rates on the moon, astronomers can estimate how often asteroids threaten Earth. Those same shadowed craters might one day supply water for lunar bases, turning the moon into a stepping stone for deeper space exploration. And because solar radiation tattoos the lunar surface over time, future missions could analyze how often the sun erupts in deadly storms, critical data for protecting astronauts. So next time you gaze at the moon, remember, you're not just seeing a rocky sphere. You're looking at a 4.5 billion-year-old diary, its pages filled with the solar system's most explosive chapters. Every crater is a sentence, every lava flow a paragraph, waiting to be read by whoever dares to explore its silent surface. What if the ultimate cosmic joke is that we've been here before, that the universe isn't just expanding but secretly folding back on itself like a Möbius strip made of spacetime? Some cosmological models suggest time might not be a straight arrow but a loop, where the far future curves inexplicably back to the Big Bang, resetting the cosmic clock for another cycle. This isn't science fiction, It's a serious possibility arising from the math of closed universes' hypothetical cosmos where space isn't infinite but curves gently in on itself, like the surface of a four-dimensional balloon. If such a universe collapses under its own gravity in a big crunch, the sheer density could trigger a new bang, birthing another cycle where galaxies, stars, and life arise all over again. Picture a cosmic record player where the needle lifts at the end of the album only to drop back at the beginning, replaying the same symphony with subtle variations. In this scenario, black holes from a prior cycle might have seeded the initial conditions for our own universe, their evaporated remnants imprinting faint patterns on the cosmic microwave background. Theoretically, if the cycles continued long enough, every possible arrangement of particles would eventually recur, meaning somewhere in the chain of universes, an identical version of you might be reading these same words, trapped in an endless cosmic déjà vu. But how would a closed universe loop time? The key lies in Einstein's equations, which allow spacetime to curve so severely that world lines, the paths objects take through time, could circle back like strands in a braid. In such a universe, traveling far enough in one direction would eventually bring you back to your starting point, not just in space but in time. Events wouldn't just resemble the past, they'd literally be the past, with the heat death of one epoch feeding the fiery birth of the next. Some versions of this idea, called conformal cyclic cosmology, propose that as our universe expands to near nothingness, its ultra-thin spacetime could mathematically reset to Big Bang conditions, like a phoenix made of equations. Critics argue that entropy should prevent true cycles. Each new universe would start with more chaos than the last, like a photocopy of a photocopy degrading over iterations. Yet proponents counter that quantum fluctuations or exotic states during a big crunch might somehow reset entropy's clock. Others suggest time loops could exist without full universes repeating, like a garden hose kinking back on itself at microscopic scales, creating tiny causal circles within an otherwise linear timeline. The implications are staggering. If time loops, free will becomes a hall of mirrors with choices both predetermined and endlessly reiterated. The cosmic microwave background might hide faint imprints of a previous cycle's black holes, like ghostly fingerprints on the dawn of time. And if civilizations could somehow survive a big crunch, they might carry memories or myths of cycles past, etched into the fabric of reality itself. For now, the evidence remains speculative, but if the universe is a loop, we're not just stardust, we're echoes of a cosmic refrain, playing on repeat across the grandest scales imaginable. Atomic clocks have become so precise they can detect time warping under the gentlest of cosmic nudges, like measuring how gravity slows time between shelves on a bookshelf. These aren't your grandfather's pendulum clocks. Modern optical lattice clocks, which trap atoms with lasers and measure their vibrations, are accurate to within 1 second over 15 billion years longer than the universe has existed. Their precision reveals a staggering truth. Time flows differently between your head and your feet. Take the experiment at the University of Colorado's Gila lab, where physicists placed one atomic clock just 33 centimeters, about a foot, higher than another. After running for just 24 hours, the higher clock ticked ever so slightly faster, gaining around 90 nanoseconds. That minuscule difference matched Einstein's predictions perfectly. The lower clock, experiencing a hair more of Earth's gravitational pull, lagged behind like a tired runner. At this scale, time isn't just relative, it's fractured, with every centimeter of altitude offering a tiny escape from gravity's temporal drag. These clocks don't just prove relativity, they turn everyday places into time-warped landscapes. A clock on the 3rd floor of a building ticks faster than one in the basement. Your upstairs neighbor is technically living further in your future by about a billionth of a second per day. Even leaning your head against a wall introduces a measurable time shift as the extra mass slightly bends spacetime around you. It's as if the universe has an invisible gradient of time, with each step you take nudging your personal clock into a new speed. The implications stretch far beyond labs. Atomic clocks aboard satellites already correct for relativity to keep GPS accurate, but next-generation optical clocks could detect underground voids by spotting subtle time-speed variations caused by missing mass. They might even hunt for dark matter. If mysterious particles interact with Earth's gravity, clocks could sense the resulting space-time ripples. Some proposals suggest using networks of these clocks as colossal detectors for gravitational waves, turning entire continents into ultra-sensitive cosmic observatories. Yet the weirdest application might be redefining the kilogram. Traditionally based on a physical platinum iridium cylinder in Paris, the kilogram could soon be defined using time itself. By measuring how much energy it takes to vibrate atoms in an electromagnetic field, scientists can link mass to time with insane precision. In this brave new world, a second isn't just a unit of time, it's a fundamental building block of reality, woven into the fabric of weight, space, and gravity. So next time you check the clock, remember, those ticking seconds aren't just marking time. They're tracing the invisible contours of space-time itself, warped by everything from mountain ranges to the shoes on your feet. The universe's clockwork is far more intricate than we ever imagined, and we're only just learning to read it. Those first fleeting moments after the Big Bang weren't just hotter and denser, they literally unfolded in slow motion compared to time today. This bizarre temporal distortion comes straight from Einstein's playbook. Where gravity is unimaginably strong, time grinds to a crawl. Picture the newborn universe as an infinitely compressed singularity, its density so extreme that space-time itself was stretched thin like taffy. In those initial minutes, the sheer mass energy of everything in existence, all the future galaxies, stars, and planets still trapped in a searing plasma, created a gravitational field that warped time so severely that a single second back then might equal hours by our current cosmic clocks. Here's why this matters. When we peer back to cosmic dawn using telescopes like Hubble or JWST, we're not just seeing ancient light, we're glimpsing epochs where time itself flowed differently. The universe's first 3 minutes, when protons and neutrons fused into the first atomic nuclei, weren't 3 minutes as we'd measure them now. From our perspective, that nucleosynthesis unfolded in excruciatingly stretched slow motion, like watching a supernova explosion frame by frame. This time dilation was so extreme that processes we associate with fractions of a second today, particle collisions, quantum fluctuations, took what we'd perceive as prolonged durations. The math behind this is staggering. General relativity predicts that time slows near massive objects, and the early universe was essentially one gigantic object of near infinite density. If you could somehow survive in that primordial soup, your wristwatch would tick glacially compared to a clock in today's sparse cosmic voids. Even photons racing at light speed would appear to crawl when viewed from our modern, low-gravity vantage point. This explains why the cosmic microwave background, the afterglow from 380,000 years after the Big Bang, still feels recent in cosmological terms. The universe's brutal early gravity stretched those first photons' journey into an eon-long odyssey. Astoundingly, we can still detect echoes of this time warp. The ratios of hydrogen, helium, and trace lithium in today's universe match calculations that account for this gravitational time dilation during nucleosynthesis. If time had flowed at today's rate back then, particle interactions wouldn't have lasted long enough to forge these elements in the observed quantities. It's as if the universe's own clocks had to slow down just to cook the first atoms properly. The implications ripple outward. Some theories suggest that black holes, those modern-day echoes of the Big Bang's density, might harbor similar time distortions in their cores. If the singularity at a black hole's heart shares properties with the infant universe, time there could grind to a near halt, stretching seconds into millennia from an outsider's view. Even dark matter, that elusive cosmic glue, might cluster in ways that subtly warp time's flow on galactic scales, though we've yet to build clocks sensitive enough to detect it. So when cosmologists say the early universe was different, they're not just talking about temperature or composition. They're describing a reality where time itself wasn't yet the steady river we know, but a viscous, molasses-like stream, thick with the weight of existence struggling to unfold. The miracle isn't just that we understand this, it's that the universe transitioned from those warped beginnings to the orderly ticking of atomic clocks we rely on today. Every second that passes now is a relic of that primordial slowdown, stretched and smoothed across 13.8 billion years into the dependable rhythm we call time. What if time's relentless march forward isn't woven into the fabric of the universe but stitched together by your own mind? This startling idea turns physics on its head, suggesting that the flow of time might be less a cosmic rule and more a side effect of consciousness itself. Think about the way a dream can compress hours into seconds or stretch moments into eternity. Your brain doesn't just perceive time, it constructs it, weaving sensory inputs, memories, and anticipations into what feels like a continuous stream. Neurologists have found that during traumatic events, the amygdala kicks into overdrive, recording extra details that create the illusion of slowed time. But here's the twist, the event didn't actually last longer. Your brain just manufactured more frames in hindsight, like a movie editor stretching a scene by adding extra shots. This isn't just psychology, it's quantum mechanics whispering something profound. At the subatomic level, particles don't seem to care about past or future. Equations describing their behavior work equally well whether time flows forward or backward. Yet in our macroscopic world, shattered teacups never reassemble, and you never meet a teenager growing younger. This jarring disconnect is called the arrow of time problem, and some scientists suspect consciousness might bridge the gap. The theory goes, without an observer to crystallize quantum possibilities into concrete events, time might not flow at all. The universe could be a vast, timeless tapestry where every moment exists simultaneously until a conscious mind slices through it, creating the illusion of sequence. Consider the infamous delayed choice quantum experiments, where particles appear to retroactively change their behavior based on future observations. It's as if the present moment is negotiating with the future, blurring the line between cause and effect. Philosophers like Julian Barber argue that what we call time is just a series of static nows, like frames in a film strip. The movement between them, that's your brain's storytelling, stitching static snapshots into a narrative. Even memory plays tricks. Your recollection of last week's dinner isn't a direct replay but a reconstruction, edited every time you access it. The implications rattle our understanding of reality. If time is a mental construct, then free will takes on new dimensions. Your choices might not carve paths through time so much as time emerges from your choices. Some interpretations of quantum mechanics go further, suggesting that consciousness collapses probability waves into reality, meaning the present moment is quite literally brought into existence by observation. It's a modern twist on the old philosophical riddle. If a tree falls in the forest with no one to hear it, does it make a sound? The radical answer, without a witness, does it even happen at all? Yet critics push back hard. If consciousness creates time's flow, why do atomic clocks, mindless machines, measure consistent time dilation near black holes? Why does entropy increase uniformly across the cosmos, independent of observers? Defenders counter that these phenomena might be the scaffolding upon which consciousness builds its illusion, like an operating system running in the background while we experience the user interface of now. The debate rages, but one thing's clear: time feels real because your brain insists it is. Every memory, every plan, every heartbeat reinforces the story. A tale where you're both the narrator and the protagonist, hurtling through a dimension that might not exist until you notice it. So next time you glance at a clock, consider this. those ticking seconds might be less about the universe's rhythm and more about your mind's relentless need to make sense of chaos. Time's arrow could be a psychological compass pointing not toward some fundamental truth but merely the next chapter in the story you're telling yourself. The past and future may be inventions, convenient fictions that let you navigate a reality far stranger than it seems. The universe might not just fade into cold, silent darkness, it could witness the literal end of time itself. Among the most chilling scenarios cosmologists entertain is the concept of heat death, where entropy reaches maximum and every last drop of usable energy dissipates into an icy, uniform void. In this state, not a single star flickers, no black hole radiates, and even the most fundamental particles slow to a near standstill. But here's where it gets eerie. Without energy, gradients, differences in heat or motion that drive change, the very concept of before and after loses meaning. Causality, the bedrock of time's arrow, crumbles, no events occur, so nothing distinguishes one moment from the next. The universe doesn't just die, it enters a state where time becomes an empty label, like a clock frozen in a featureless void. Yet heat death isn't the only apocalypse that could erase time. Lurking deeper in quantum field theory is an even more abrupt doomsday, vacuum decay. Imagine the fabric of reality is like a ball resting in a valley. Our current laws of physics represent the lowest energy state, keeping the ball stable. But what if there's a deeper valley hidden beyond the hill? A quantum fluctuation could theoretically knock the ball over the ridge, unleashing a bubble of true vacuum, where the fundamental constants of nature, like the speed of light or the strength of gravity, rewrite themselves instantly. This bubble would expand at light speed, erasing the old universe in its wake. But the true horror isn't just the annihilation of matter, it's the destruction of space-time's structure. If the new vacuum alters how particles interact, causality might shatter mid-process. An observer, if one could exist, might see effects precede causes, equations unsolve themselves, or time fracture into incoherent fragments before ceasing entirely. Strangely, these scenarios reveal time's fragility. We think of it as an immutable backdrop, but physics treats it as a dynamic player dependent on energy, entropy, and the universe's quantum scaffolding. Remove those supports and time doesn't just slow or warp, it vanishes like a shadow at noon. Even black holes offer previews of this. At their singularities, general relativity predicts infinite curvature, where space-time equations break down and time becomes undefined. The universe's finale could be a wholesale unspooling of that same fabric everywhere at once. Perhaps the most humbling thought: if time ends, there won't be anyone to notice. No clocks will stop ticking because there'll be no ticks to measure. No final moment will be recorded, just an infinite, eventless after without observers, memories, or meaning. The ultimate cosmic punchline: the end of time might be the one event that, by definition, never actually happens. It's not a point in time, it's the absence of time itself. And that's far stranger than mere oblivion. We've journeyed through a universe where time stretches, loops, and even shatters, where black holes freeze moments into eternity. Quantum particles rewrite history, and twin astronauts age apart like characters in a sci-fi novel. We've seen how Mercury's day outlasts its year, how your head literally ages faster than your feet, and how the present you perceive is always a nanosecond behind reality. The cosmos operates on timescales so vast that civilizations could rise and fall in the blink of a galactic eye, while distant galaxies race away faster than their light can reach us, erasing entire epochs from view. Yet amid this temporal chaos, a profound irony emerges. All these mind-bending truths, time crystals that dance without energy, universes where cause and effect flip, even the potential end of time itself, are discovered by creatures who live mere decades. Our lifetimes are less than cosmic eye blinks, yet we've decoded relativity, measured time warps between floorboards, and sent clocks into space that return younger. The universe may play with time like putty, but we're the ones who noticed. So as you check your watch today, remember, those seconds ticking by are threads in a tapestry woven from the Big Bang to black holes. Your heartbeat syncs with pulsars, your breath echoes supernova remnants, and every thought you have unfolds against spacetime's ever-stretching canvas. The universe doesn't just bend time, it invites us to marvel at its contortions. Now we'd love to hear which cosmic time fact shattered your reality the most. Was it the astronaut twins aging apart or the quantum particles changing the past? Drop your mind-blown moments in the comments, and if you've enjoyed this temporal roller coaster, hit subscribe for more voyages to the edge of reality. The universe's clock is ticking, but here, the wonders never stop.